linear systems application problems. So we've done a lot of work with linear systems, and now we're going to take a look at some application problems for which we can use linear systems to solve them. Okay, so what do we know coming in? We know what a linear system is. It is two or more linear equations working together. And here's an example. We've been working with a system of linear equations in two variables, like this one. And we know that linear systems can be solved graphically by the substitution method and by the addition method. We're going to make use of two methods today. We're going to make use of in this video, the addition method and the graphing method. Okay, anytime you're dealing with two related equations and two unknowns, well, you're talking about a linear system in two variables. And so we're going to take a look here at a couple of application problems that can be solved using linear systems. Our first example is something that I can remember teaching in middle school. We taught it a little differently. We certainly did not use linear systems in middle school, but in the pre-algebra class, we were able to set this problem up and then solve it using some pre-algebra methods. Okay, so example 1. 3 times a first number decreased by a second number is equal to 1. The first number increased by twice the second number is 12. Find the two numbers. Again, so in pre-algebra, we used one unknown and we came up with two equations. Here, we're going to use two unknowns and solve it using linear systems. So we first want to note and let x equal the first number and let y equal the second number. Now, you may remember from previous math classes that as soon as you have two unknowns, you're going to need two equations to solve them. Two unknowns require two equations to solve them. So let's create our system. All right, 3 times a first number, so 3 times x, since x is our first number, decreased by, that's subtraction, a second number decreased by y, because y is the second number, is, that's the equal sign, 1. So there's our first equation. 3 times the first number decreased by a second number is 1. Our second sentence, the first number, that's x, the first number, increased by would be plus, twice the second number, so that would be 2y, is 12. So the first number increased by twice the second number is 12. So that takes you back to some of those earlier math days, translating number sentences into mathematical equations. Okay, well, I'm looking at this, and I'm going to solve this by addition because I see that it's pretty easy to multiply the second equation. Let's make a note here. That's the first equation, that's the second equation. I can multiply the second equation by -3, and I'll have opposite coefficients. Or I can multiply this first equation by +2, and I'll have opposite coefficients for the y variable. I'm going to choose the first. I'm going to multiply equation 2 by -3. So that means this equation, I'm going to have no change. I'm going to leave it alone. So let's just copy it over. 3x minus y is equal to 1. The second equation, I'm going to multiply it by -3. And when I do that, -3 times x is -3x. -3 times +2 is +2y, is -6y. And -3 times 12 is -36. Now I can add. And it's just as I wanted to happen, In this case, my x terms zero out. And when I add my y terms, a negative y plus a negative 6y is a negative 7y. And a 1 plus a negative 36 is a negative 35. I now have one equation in one unknown. Well, that's easy to solve. I'll divide both sides by negative 7, and I get y is equal to 5. So I feel pretty certain that the second number of these two numbers is positive 5. Let me slide up here for you. What's the first number? Well, we'll just put positive 5 into either equation 1 or equation 2 to solve for x, which is the first number. I'm going to use equation 2. And equation 2 says x plus 2 times y. I'll replace the y with a 5 is equal to 12. Well, 2 times 5 is 10. So x plus 10 is equal to 12. Subtract 10 from both sides. And x, which, subtract 10. I was talking too quickly. So x, which represents the first number, is equal to 2. So my proposed solution is the first number is 2, and the second number is 5. And you can check it. Of course, you're going to want to check it, but we can probably check this one pretty quickly mentally. 3 times 2 is 6. 6 minus 5 is 1. That was pretty simple. This is x, so 2 plus 2 times 5. Well, 2 times 5 is 10. 2 plus 10 is 12. So there's a quick, I just did that check in my head because these equations aren't too bad. So that's kind of a application problem, or at least maybe that's more like a word problem, not particularly an application problem. But that certainly is something you've probably seen in your pre-algebra days as you work to solve some of these similar types of algebra problems. Let's take a look at a business application here. So give me a moment to flip my paper over, and let's take a peek here. So in business, and my paper's crooked. Let's try this again. I think my paper's crooked. There we go. Hope that's better. In business, we talk about having a break-even analysis and a break-even point. So in business, the break-even point is the point where you are not making money, but you're also not losing money. So you're breaking even, okay? You're not losing, and you're not making. So you're breaking even. And obviously, you want to be to the right of the break-even point. You want to be making money. You don't want to be to the left of the break-even point where you're losing money. And we'll see that with our graphing calculator. So it's a good example of the use of linear systems. Let's take a look. I kind of made this one up. We got a company that wants to make some fancy candy bars. And they've determined that their fixed costs are going to be $5,000. The machinery, how much they're going to pay their employees, that type of thing. The utilities, the lights, their fixed costs will be $5,000. And it's going to cost $4 in variable cost to produce each candy bar. So this is things like the sugar and the chocolate. Okay, your fixed costs will always be there. You know, renting the facility, buying the machinery, those are fixed costs. But the amount of chocolate and the amount of vanilla, maybe milk, you're going to use to make these chocolate bars is a variable cost. Okay, and then when they go to sell them, each candy bar is going to be sold for $7. So let's write the cost function, letter A. Okay, so the cost function, and I'll denote this since we're using C. The cost is a function of the number of candy bars. C of X, put number of candy bars in, get the cost out. Well, it's going to cost us $5,000 in fixed cost, plus every candy bar is going to have $4 of variable costs. Again, things like the cocoa, things like the milk, that type of thing to make these fancy candy bars. Okay, so this is their costs. Okay, letter B. Whoops, I used a period. This should probably follow follow the pattern. What is the revenue function? How much money am I bringing in? Well, the revenue is also a function of the number of candy bars. It's a function of the number of candy bars sold. And I bring in $7 for every candy bar, 7 times X. Okay, so we have a linear system here, two equations, okay, that are related. We can write this one as with our fancy bracket or curly bracket, and we can say that, and for the cost function, y, the output, is 5,000 plus 4 times x. Maybe you can call that y1 if you want, because our calculator uses a y1 and a y2. y2 is equal to 7 times x. So these are two lines, and we want to figure out where they break even, where they intersect in a linear system. So I'm thinking, because equation 1 is a y equal and equation 2 is a y equal, let's just graph it. That's by far the easiest way. So letter C, determine the intersection point. Let's use the graphing technique to find the intersection point. That's a whole lot easier than doing any substitution or any addition. So I'll go to my graph. And let's see here, y equals. My first one is 5,000 plus 4 times x, and that's the cost function. The second one is simply 7 times x. Now, we're in the real world. We're selling candy bars. We know we're going to spend $5,000 in fixed costs. So we're going to need, we simply can't go to our standard window. Zoom 6 is our standard window. We're not going to see much, okay, because we're outside of the standard window. There's one of the, there's this function, but we're not even seeing this one. We're seeing the revenue function, but we're not even seeing the cost function. Now I know from kind of playing around with this, I'm going to go to my window, and I'm in the real world, so I'll start at 0. 0 candy bars are sold, and I'm going to go as high as 2,000. So we're going to on the x-axis, we're going to go from 0 candy bars that are sold to 2,000 candy bars that are sold. And since I'm going to 2,000, I'm going to go ahead and count by 500s on my axis. This makes it a little bit neater. Now my revenue, well, I surely am hoping I'm making more than $5,000 because I want to try to make some money here. I know my fixed costs are $5,000. But I know there's not going to be any negative revenue going in, so let's put 0 in for the negative. Again, we're in the real world, so we're in quadrant 1. And I'm going to go as high as $20,000. And again, I kind of know, I do know the answer to this problem. You may have to do a bit more playing with this till you see the intersection point, but I already know what the answer is. If I'm going to count from 0 to 20,000, if I'm going to go from 0 to 20,000, I might as well count by 5,000. So now if I graph, there's my cost function, and there is my revenue function. So my cost for no candy bars, I'm going to spend $5,000 just for the facility and the equipment. And then as I use up cocoa and I use up milk and whatnot, sugar, my costs will increase along this line. And you can see my revenue starts out at 0. If I sell no candy bars, I have no money coming in. But $7 for every candy bar, my revenue is climbing up a little quicker than my costs are climbing up. And right here is an intersection point. Okay, so let's go to our intersect, so second calc, and go to number 5 for the intersection point. And again, is the cursor on the first curve the blue curve? Yes, it is. Press enter. Is the cursor on the second curve, which in my case is the red curve? Press enter. The calculator is asking you to guess the intersection point. Well, of course, I want you to do that. Press enter. And it says they intersect, and I'm going to round this to the nearest integer. They intersect at 1,667 candy bars, and the money coming in is $11,667 to the nearest whole dollar. So, determine the intersection point. Intersection point is 1,667. That's X. So that's the number of candy bars. And the money coming in, the cost or the revenue at that number of candy bars, we saw was $11,667. So that's the intersection point. I guess I should note that this is candy bars because I noted that the Y variable was money. Okay, so what does it mean? Well, this tells us when 1,667 candy bars are sold, both the cost and the revenue are the same. And we saw that because it's an intersection point. Let me slide this up for us a little bit. Are the same. And that is $11,667. Okay? So when cost equals revenue, and I'll abbreviate when cost equals revenue, this is the break-even point. Okay, and which means the break-even point means you're not losing money, but you're also not making money. Whoops, not losing money, but not making money. You're breaking even. Your income equals your expenses, but not making money. Okay? And if we look at the graph, go back to the graph. All right, if we're to the left of the break-even point, the blue line, which is the cost, exceeds the red line, which is the revenue. So to the left, we are losing money. Our costs are higher than our revenue. To the right of the break-even point, our revenue, the red line, is above the blue line, the cost. And so we want to be to the right. We want to be making money. We don't want to be losing money. Okay, so fewer candy bars. Fewer candy bars sold than the 1667 tells us we're losing money. That's not a good place to be. Okay. However, more candy bars sold, again, over 1,667 candy bars sold, that tells us that we are making money, and that is where we want to be. Okay, so there's a couple of examples of when you can use a linear system of two equations and two unknowns to kind of give you some answers. One to just kind of a word problem, and the second one here to kind of a business problem where they look at what is the break-even point in business. It's very important to understand that so that you're making money and not losing money.